Laplace transformer. L of f of t is equal to the integration of f of t times e to the negative st from 0 to infinity. It has to fulfill two sufficient conditions. F of t is a piecewise continuous function on the interval from 0 to a, and the absolute value of f of t must be less than or equal to k times e to the at, where t is greater than or equal to m for any real constant a and some positive constants k and m. Any transformations on the function of time means you change the frequency domain. Here are some basic functions. T to the power of n is equal to n factorial over s to the n plus 1. E to the negative at is equal to 1 over s plus a. T times e to the negative at is equal to 1 over s plus a squared. You can get this by taking e to the negative at and taking its negative differentiation in relation to s. So that means that t to the n times e to the negative at is equal to n factorial over s plus a to the power of n plus 1. Sine of bt is equal to b over s squared plus b squared. Cosine bt is equal to s over s squared plus b squared. And then you have the same function with e to the at being a phase shift. So e to the negative at times sine bt is equal to b over s plus a squared plus b squared. And then the same thing with cosine. There are some useful properties to remember when using Laplace transformer. L of f differentiated n number of times is equal to s to the n times the Laplace of f minus s to the n minus 1 times f of 0, all the way down to the final differentiation. We get this by taking the Laplace transformer of a differentiation of f of t. So we input that in to be the integration of e to the negative st times f prime of t from 0 to infinity. We plug this in. Using integration by parts, we get the first part is e to the negative st times f of t from 0 to infinity, minus the integration of f of t times negative s e to the power of negative st dt from 0 to infinity. So the Laplace transformer of f prime of t is equal to f of infinity over e to the infinity, which goes to 0, minus f of 0 over e to 0, which goes to f of 0, plus s Laplace transformer of f of t. So this means that the Laplace transformer of f prime of t is equal to negative f0 plus s Laplace transformer of f of t. This pattern continues for all higher derivatives. Frequency shift. So when you take the Laplace transformer of f of t times e to the at, this means that it creates a phase shift of f of s minus a. So you have the Laplace transformer of e to the at times f of t. That is equal to the integration of e to the negative st times e to the at times f of t integrated in relation t from 0 to infinity. We then group the e to the power of's together, so it becomes the integration of e to the negative s minus at times f of t integrated in relation to t from 0 to infinity. We use substitution so that u is equal to s minus a, so it becomes the integration of e to the negative ut f of t dt from 0 to infinity is equal to f of u, which is then equal to f of s minus a. We then have the time domain integration, which is the Laplace transformer of a function integrated from 0 to some t of f of u du is equal to f of s over s. We get this by letting g of t equal to the integration of f of u du from 0 to t. So that means the Laplace transformer of g prime of t is equal to the Laplace transformer of f of t. And using what we discovered earlier, this is then equal to the S of Laplace of g of t minus g initial is equal to f of s. We then have the frequency domain differentiation. So we have the Laplace of t to the n times f of t. We then find that this is equal to the negative 1 to the power of n differentiated n number of times of f of s. We see that t of f of t is equal to the integration of e to the negative st times t of f of t in relation to t from 0 to infinity is equal to the negative derivative of e to the negative st times f of t dt from 0 to infinity. We then take the negative d of s out, so it becomes the negative integration of e to the negative st f of t in relation to t from 0 to infinity, which is then equal to the negative derivative of f of s. Using this one, you can go from a constant and just keep taking the derivative of it until you get the proper value for various values of t. Remember that the value of a constant will be the constant over s. You keep taking the differentiation of that, you'll get any power of t to the n. Next we have time scaling. The Laplace transform of f of at is equal to 1 over a f of s over a. We can see that in the Laplace transform of f of at is equal to the integration of e to the negative st times f of at dt from 0 to infinity. We substitute z to be equal to at, so that the Laplace transform of f of at is equal to 1 over a times the integration of e to the negative s over a z f of z dz from 0 to infinity, which is akin to the Laplace transformer of f of at is equal to 1 over a f of s over a. We then have the frequency domain integration. We have Laplace of f of t over t is equal to the integration of f of u du from s to infinity. We substitute g of t to be equal to f of t over t, so that the Laplace transformer of f of t is equal to the Laplace transformer of t g of t. We then take both sides, and using the previous information we find that this is equal to f of s is equal to the negative differentiation of the Laplace transformer of g of t. We isolate the s variable and integrate, so it becomes the integration of d Laplace transform of g of t is equal to the negative integration of f of s ds. So the Laplace transformer of g of t is equal to the negative integration of f of u du from infinity to s, so that the Laplace transformer of f of t over t is equal to the integration of f of u du from s to infinity. As we stated before, now we have L of sine of omega t is equal to omega over s squared plus omega squared. We then take the differentiation of that, so it's the Laplace transformer of d dt of sine of omega t is equal to s times omega over s squared plus omega squared minus sine initial, which is then equal to s omega over s squared plus omega squared. Using the frequency domain differentiation property, you can go the opposite direction. So we have the Laplace of sine of omega t is equal to omega over sine squared plus omega squared. We then find the Laplace of this t sine omega t is equal to the negative differentiation of omega over sine squared plus omega squared, which is then equal to 2 omega s over s squared plus omega squared squared.
Now, as with any linear transform, the Laplace transform has a property of distributing across things that are added or subtracted from each other. For example, the Laplace transform of f of t plus g of t is just the Laplace transform of f of t plus the Laplace transform of g of t, where we're evaluating the Laplace transform of each function separately and then adding it together. Now let's do an example of this where we have the Laplace transform of t squared minus 2 e power negative 2t plus sine of 3t. we can distribute that Laplace transform across each individual function and evaluate it separately. And then finally, we can add them together to find that 2 over s cubed minus 2 over s plus 2 plus 3 over s squared plus 9 is the final answer. Let us now talk about the Laplace transform of periodic functions. If f of t is piecewise continuous on the interval 0 to infinity of exponential order and periodic with period t, then the Laplace transform of f of t is defined as 1 over 1 minus e power negative st times the integral from 0 to t e power negative st times f of t dt. Given in front of you is a simple proof on how this equation has been solved, and very soon we will be doing an example from this proof. In the first line of the proof, we have the Laplace transform of f of t equals from the integral 0 to t e power negative st times f of t dt plus t to infinity e power negative st f of t dt. If we let t equal u plus t, we can evaluate this integral and we will find that the Laplace transform of f of t is just 1 over 1 minus e power negative st times the integral from 0 to time period e power negative st f of t dt. Let us now do an example of the Laplace transform of a periodic function. For convenience, let us assume that our function f of t equals 3 sine of t, where one oscillation of sine of t for one of the time period of this function is t equals 2 pi. Now, the Laplace transform of f of t equals 1 over 1 minus e power negative 2 pi s times the integral from 0 to 2 pi e power negative st times 3 sine of t dt. Evaluating this integral via integration by parts leads us to get 3 over s squared plus 1 times 3 e power negative 2 pi s squared plus 1. Taking 3 common in the numerator, we notice that the 1 minus e power negative 2 pi s term cancels, and we are left with the Laplace transform of 3 sine of t equals 3 over s squared plus 1, which is what we would expect if we were just taking the Laplace transform of 3 sine of t. Now is a convenient time to introduce the inverse Laplace transform. The Laplace transform is a linear operator since it acts as a one-to-one transform, and hence it must have an inverse transform. The inverse Laplace is often written as L with the negative 1 on top of f of s, which operates on f of s to convert it back into the time domain to f of t. There must be some condition on f of s for it to be transformed. This condition is that the Laplace inverse of f of s must exist if the limit of s approaches infinity of s over s squared plus 1 tends to 0. Now, to prove that the Laplace inverse transform is a linear transform, let us look at this proof. The Laplace inverse of f of s plus g of s is equal to the Laplace inverse of the Laplace of f of t plus g of t, because of the linear transformative property of the Laplace transform. The Laplace inverse and Laplace transform cancel, hence proving that the Laplace inverse is a linear transform. To exercise this, we are going to do this example of the Laplace inverse of s plus 1 over s times s minus 4, where we can use partial fractions to split up the s and s minus 4, and then use the linear property of the Laplace inverse to operate on each function individually and combine them in the end to get minus 1 over 4 plus 5 over 4 e to the 4t. This is the inverse Laplace function. Let us now talk about an alternative method to solving the Laplace inverse of a function f of s, other than using the method of partial fractions, which can sometimes be tedious. The residue theorem, which we have seen in its derivative form, is actually a simplification of Bromwich's complex inversion integral. The function f of t is to be equal to the sum of the residues of f of s, which is evaluated individually by the given formula, where we take the limit of s approaches a, 1 over n minus 1 factorial, the derivative dn minus 1 ds power n minus 1 of s minus a to the power n e to the power negative st times r f of s, where n is the power of s plus a term in the denominator of f of s. What if we wanted to take the Laplace transform of a function f of s equals 1 over s times s plus 2, where we have two simple poles, one at 0 and one at negative 2? Well, then we could evaluate the residue theorem at each individual pole, which would yield 1/2 at s equals 0 and negative 1/2 equals negative 2t at s equals negative 2. But what if instead we had a function f of s equals 1 over s plus 1 times s minus 2 whole square, where it is given that one simple pole is at s equals negative 1 and we have one double pole at s equals 2? Well, then we can evaluate the residue theorem at s equals negative 1 as done before, but when evaluating the residue theorem at s equals 2, we have to use n equals 2, hence taking the derivative of the term within the brackets, which yields the answer 1/3 times t to the power e power 2t minus 1/9 e power 2t. The gamma function is a form of the metagene transform, which is the integral that goes from 0 to infinity f of t power alpha minus 1 dt, where for the gamma function, f of t is defined as e power negative t, and so it is the integral of 0 to infinity e power negative t power alpha minus 1 dt, and this is the gamma function. Let us demonstrate proper usage of the gamma function by trying it out in this example. Here is it required that we prove that gamma of alpha equals 1/2 is equal to root pi, or radical pi. We can begin by substituting alpha equals 1/2 in the previous equation, which upon simplifying becomes the integral 0 to infinity e power negative t power negative 1/2 dt. To solve this integral, we have to now use the u substitution where t equals u squared and 2u du equals dt. We transform this integral into a space where the integral is now 2 times the integral 0 to infinity e power negative u squared du. Upon reaching this step, then now the trick is to let this integral equal some variable I. Now notice to integrate to integral 0 to infinity e power negative u squared du, we have to make a u substitution to get rid of the u squared. But we cannot do so because there is no additional u term in the integral as it is. So the trick we use is to square both sides, where our integral now becomes I squared equals from 0 to infinity, 0 to infinity, e power negative y squared plus x squared dx dy, which can now be seamlessly converted into polar coordinates, where I squared equals 4 times 0 to power over 2 for theta, 0 to infinity for r, where x squared plus y squared equals r squared, and where dx dy becomes r dr d theta. Now, upon isolating variables, we can now integrate each respective component, which gives us I squared equals pi upon simplification and I equals root pi upon square rooting, or that gamma of 1/2 equals root pi. A very important function of the gamma function is its use with the Laplace transform when solving for t power n, where n is not a whole number. Here, the Laplace transform of t power n can be rewritten in the form of the gamma function, where alpha equals n plus 1 divided by s power n plus 1. For example, when we're evaluating the Laplace transform of the tricky function t power 1/2, we can use the previous theorem to rewrite it in the form of gamma 1/2 plus 1 divided by s power 1/2 plus 1. Using the fundamental rule of the gamma function, gamma of n plus 1 equals n times gamma of n, which makes the function in the form as shown in front of you guys, and can be easily evaluated by the substitution of gamma 1/2 equals root pi, which leads us to conclude that the Laplace transform of t power 1/2 is simply root pi over 2 times s power 3/2. Sometimes when we're evaluating the Laplace transform of t power n, it becomes rather difficult to evaluate this function using the gamma function, because gamma function will only help you go back one step at a time using the fundamental theorem, which is gamma n plus 1 equals n times gamma n. And so in such cases, it is somewhat nifty to have this relation in mind, where the Laplace inverse of 2n minus 1 double factorial times root pi divided by 2n times s power n plus half equals t power negative 1/2. And this equation might look daunting because you guys might not have seen the double factorial before, but the double factorial is just a piecewise function defined where when n is greater than 0 and is odd is just n times n minus 2 times n minus 4, 5, 3, 1. When n is greater than 0 and is even, it is n times n minus 2 times n minus 4, 6, 4, 2. And when n is equal to 0 or 1, 2n minus 1 double factorial is just 1. I will demonstrate the proper usage of this new theorem in the time to come. Let us now try to evaluate what the Laplace transform of t power 1/2 is using the theorem that we have learned before, the double factorial. Now, if we substitute n equals 1 into the previous equation, we find that on the right hand side, the equation of t becomes t power 1/2. And on the left hand side, we have the Laplace inverse of 2 minus 1 double factorial times root pi divided by 2 power 1 s power 3/2 equals t power 1/2. Upon simplifying, we have the Laplace inverse of root pi over 2 times s power 3/2 equals t power 1/2, where the double factorial of 1 from our piecewise function is just 1. Now, taking the Laplace transform on both sides, we find that the Laplace transform of t power 1/2 is just root pi over 2 times s power 3/2, where the Laplace inverse cancels on the left hand side. Now this result is consistent with the results we got from the gamma function, but is rather useful because we can substitute it for any power of n. The unit step function is a handy piecewise function in that it allows us to model a function as if it was being turned on and off by a switch. The unit step function is defined to be equal to 0 at all values of t less than a and 1 at all values of t greater than a. There is a discontinuity at t equals a, but we often model this transition phase by logistic equations, sometimes written as the limit of b approaches infinity of 1 over 1 plus e minus 2b t minus a, where the unit step function u of t minus a is equal to half of 1 when t equals a. Let us now look at the Laplace transform of the unit step function. The Laplace transform of the unit step function is defined as e power negative as times f of s, where we can prove this by applying this as our function in the Laplace transform, where our integral goes from 0 to infinity, e power negative st times f of t, which is now f of t minus a, times the unit step function t minus a dt. We can now split this integral into two parts, one from 0 to a and one from a to infinity. The 0 to a integral goes to 0 because the unit step function equals 0 for this interval. At all values greater than a, the unit step function just equals 1. So now we only have to evaluate the integral from a to infinity. Using the unit substitution v equals t minus a, we find that indeed the unit step function's Laplace transform is e to the power negative as f of s. Let's now also do an example. For example, what if we had the Laplace transform of sine of t minus pi over 2, which is a right phase shift, times the unit step function t minus pi over 2. It is basically the normal Laplace transform of sine of t and e power negative pi over 2s is added on top of this as a product, as is shown in front of you guys. Now, as the unit step function is defined to be equal to 0 at all values of t less than a, and 1 at all values of t greater than a, when graphing the product of the unit step function and a function f of t, the graph will be equal to f of t at all values of t greater than a, and 0 at all values of t less than a. The Dirac delta function represents an impulse function which is defined to be equal to infinity at t equals a and 0 at all other values. When integrating the Dirac delta function, it is always found that the area underneath the curve is equal to the area of a rectangle with height 1 over epsilon and a base of epsilon, which gives the integral the value of 1. When taking the Laplace transform of the delta function, we can write it in the form of an integral which goes from 0 to infinity e power negative st times the delta function dt, where f of t is now replaced with the delta function. However, since the delta function is defined to be the derivative of the unit step function, using the fundamental rule of integration, the Laplace transform of the delta function is nothing but e power negative as.
Convolution. Convolution is when you place one function onto another, and it can be represented by the formula of the f convoluted onto g of t is equal to the integration of f of tau times g of t minus tau d tau from 0 to t, for f and g are from 0 to infinity. This expresses the overlap of g as it shifts over f, bending the functions. In this case, we have a window function with a sawtooth. If you impose f of g over it, you see as it goes the overlap increases and then decreases at a different rate. And then if you do the reverse effect of g onto f, you see that it increases and then decreases at a similar rate. You have more examples of this, and shows how they behave differently on each one of them. But this one shows a box on a box and a triangle on a triangle, showing how the functions behave differently. As you can see with the box, you have a linear increase, then a linear decrease, as you can see with these overlapping boxes. Same thing with the sawtooth. You have the increase and then decrease at the same but opposite rate. Some important properties of convolution. Convolution is a commutative property, so f onto g is the same as g onto f. It is a distributive property, so f onto the quantity of g plus h will be equal to f onto g plus f onto h. It is also associative property, so parentheses don't really affect it too much, so that means f onto g onto h is equal to f onto g onto h. And it also follows the zero property, so f onto 0 is equal to 0 onto f as part of the commutative property, which is both going to be equal to 0. It is worth noting that the Laplace transformer on f of g is equal to the Laplace transformer of f of t times Laplace transformer of g of t, which would then be equal to big F of s times big G of s. A simple proof for that is as follows. You have the big F of s times big G of s is equal to the integration of e to the negative st or e to the negative s tau times f of tau d tau from 0 to infinity times the integration of e to the negative sv g of v dv from 0 to infinity. Because these are two different functions, you can then group them together and then divide them back up, so it becomes f of tau d tau integrated from 0 to infinity times e to the negative tau plus v of s gv dv from 0 to infinity. We then substitute t to be equal to tau plus v, so it then becomes 0 to infinity f of tau d tau times the integration of e to the negative ts g of t minus tau dv from 0 to infinity. We then group them back up together, so it becomes the integration, the double integration of e to the negative st f of tau gt minus tau dt from tau to infinity d tau from 0 to infinity. Using this information, we also recall that the f of onto g is equal to the integration of f of t minus tau g of tau d tau from 0 to t. Thus, we have an agreement with our original assertion. You also have the inverse for convolution. We remember that the reverse Laplace of big F of S times big G of S is equal to F onto G. We wish to determine the inverse Laplace of 1 over S minus A and then S minus times S minus B. We notice that f of s is equal to 1 over s minus a, and then g of s is equal to 1 over s minus b. It follows that f of t then must be equal to e to the at, and g of t must be equal to e to the bt. Therefore, we use the inverse Laplace of 1 over s minus a times s minus b is equal to f onto g, which is equal to the integration of f of t minus tau g of tau d tau from 0 to t is equal to the integration of e to the negative e to the a times t minus tau times e to the bt dt from 0 to t is equal to e to the at times the integration of e to the tau times b minus a d tau from 0 to t, which is then equal to e to the bt minus e to the at over b minus a. We can solve differential equations using Laplace transformers. The process is quite simple. You follow these three easy steps. You take the Laplace transformer of the differential equation, algebraically solve for the big Y of s. The solution will be the inverse Laplace transformation of big Y of s. Example, if we were to solve 2y prime plus y is equal to 0, with y of 0 being equal to negative 3, we take the transformer of that to get 2 of sy plus 3 plus y, because remember that the Laplace transformer of a differentiation of an equation will be the big Y times s of how many ever times it was differentiated minus all the different values beyond that. We then use this information to solve for it algebraically, so that big Y is equal to negative 6 over 2s plus 1, which is equal to negative 3 over s plus 1 half, which is equal to negative 3 times the Laplace transformation of e to the negative 1 half t. Using this information, we find that y of t is equal to negative 3 to the negative 1 half t, which satisfies our initial condition of y of 0 being equal to negative 3. Constructing differential equations. If we are given a solution, we can easily use a Laplace transformation to construct a differential equation that satisfies our condition. Here we're given the equation y of t is equal to c over b minus c over b times e to the negative b t minus a times the step function of t minus a. To solve for this one, first we ignore the step function and take the transformation, so that big Y of s is equal to the Laplace transformer of c over b minus c over b times e to the negative bt, which is equal to c over s times s plus b. We then multiply that back out, so it becomes s big Y plus b big Y is equal to c over s. We then place our step function back into the equation as we took it out earlier. The step function is equal to e to the negative as over s, so the entire function becomes equal to s big Y plus b big Y is equal to c e to the negative as over s. We then take the inverse transformation of both sides to find that y prime plus by is equal to c times the step function of t minus a, which satisfies our initial given solution. And then we have to also then find our initial conditions. Here we know that y of 0 is equal to 0 since we had no extra terms, no constants whatsoever. It is important to note though that if y initial is equal to k instead, the solution would become y of t is equal to c over b minus c over b e to the negative bt ta, the step function of t minus a, plus c of k over b minus ck over b e to the negative bt, as you would then have a constant that you would have to account for when you solve the problem.